I'm Parth Gandhi and I'm going to present a topic on organic solar cell that I will be covering through my presentation. Solar cell. An organic solar cell is a type of photovoltaic that uses organic electronics, a branch of electronics that deals with conductive organic polymers or small organic molecules for light absorption and charge transport to produce electricity from sunlight by photovoltaic effect. For example, polymer solar cell. Let us talk about advantages and disadvantages of organic solar cell. Solar energy is plentiful and free. Why organic instead of inorganic? There are advantages. It has low cost, high speed production, optical absorption coefficient of organic molecule is high, chemical flexibility for modification via synthetic methods. There are disadvantages as well, such as low efficiency, low stability, and low strength as compared to organic inorganic solar cell. About the working principle of organic solar cell. There are four steps involved: light absorption, exciton dissociation, charge transportation, and charge collection. First step is the light absorption leading to exciton formation. When the sunlight is directed onto photosensitive semiconducting organics, electrons in HOMO, that is highest occupied molecular orbital, are excited to LUMO, that is lowest unoccupied molecular orbital. After light absorption, organic semiconductors require additional processes to produce free carriers. First, semiconductors form excitons which are strongly bound electron hole pairs that then diffuse inside the organic semiconductor, which is independent on applied electric field. Exciton dissociation occurs only at the interface between the donor and the acceptor due to the offset of homostates of the donor and the acceptor. If the excitons do not reach the interface, they recombine, and the absorbed energy is dissipated without generating photocurrent. Therefore, to efficiently generate power, the excitons have to be dissociated and collected at the electrodes before recombination. The overall efficiency of the organic solar cell is the combination or the product of all the efficiency at each and every state, that is light absorption, excitant dissociation, charge transportation, and charge collection. Through the performance analysis of organic solar cell, it is characterized by the JV curve shown in the figure 2.a. It is dependent on four factors: short circuit current, open circuit voltage, fill factor, and power conversion efficiency. Figure 2.a shows that the current voltage product is negative and the cell generates power when the voltage is between 0 and VOC. At V less than 0, the illuminated devices act as a photodetector, consuming power to generate photocurrent that is light dependent but bias independent. At V less at V greater than VOC, the device again consumes power. This is the region where the light emitting diode operates. Power conversion efficiency can be measured as this equation. The fill factor can be measured by this equation. Overall current voltage response of the cell can be approximated as the sum of the short circuit photocurrent and the dark current density, which is given by JV is equal to J dark minus JSE. For an ideal diode, the dark current density is given as J dark is equal to J naught e raised to QV by KT minus 1. Although the reverse current which flows in response to the voltage in an illuminated cell is formally equal to the current that flows in the dark, the approximation is reasonable for many photovoltaic materials. When the contacts are isolated, VOC has its maximum value. This is equal to the condition when the dark current and the short circuit photocurrent exactly cancels out. VOC can be given as KT upon Q up into ln JSC upon J naught plus 1. Thus, VOC increases logarithmically with light intensity. Architecture. There are three kinds of device architecture for organic solar cells: single layer, bilayer, and bulk heterojunction, that is BHJ. Single layer, it is the simplest form. These cells are made by sandwiching a layer of organic electronic material between two metallic conductors, typically a layer of indium tin oxides, that is ITO, with the high work function, and the layer of the low work function metals such as aluminium, magnesium, or calcium. The basic structure of the cell is illustrated in the figure 3. The difference of the work function between the two conductors sets up an electric field in the organic layer. When the organic layer absorbs light, electron will be excited to LUMO and leaves holes in the HUMO, thereby forming excitons. The potential created by the different work functions helps to split the exciton pairs, pulling electrons to positive electrodes and holes to the negative electrodes. Bilayer cells contain two layers in between the conductive electrodes as shown in the figure 4. The two layers have different electron affinity and ionization energies. Therefore, electrostatic forces are generated at the interface between the two layers. The materials are chosen to make the differences large enough that these local electric fields are strong, which splits excitons much more efficiently than a single layer PV cells. The layer with high electron affinity and ionization potential is the electron acceptor, and the other layer is electron donor. This structure is also called planar donor heterojunction or PHJ. BHJ have an absorption layer consisting of the nanoscale blend of donor and acceptor materials. Advantage of BHJ over the layered photoactive structure is that they can be made thick enough for effective photon absorption without the difficult processing involved in orienting a layered structure while retaining the similar level of performance. After the capture of photon, electrons move to the acceptor domains, then are carried through the device and collected by one electrode, and the holes move in the opposite direction and collected at other side. If the dispersion of the material is too fine, it will result in a poor charge transfer through the layers. Most bulk heterojunction cells use two components, although there are three components which have been explored. The third component, a secondary p-type donor polymer, acts to absorb light in the different region of the solar spectrum. Talk about the ways to improve efficiency of the organic solar cell. Ideally, the organic material for OPV should have high absorption coefficient, low band gap, high stability, high mobility, solubility, and exhibit percolating morphology. Various strategies can be implemented to maximize each step involved in the photovoltaic process of OPV to enhance performance of the cell effectively. For example, light absorption can be improved by bandgap tunneling or by stacking multiple PV cells, such as tandem cells. Exciton dissociation can be improved by increasing the interface area between the donor and the acceptor. Finally, the charge mobility accepts the charge transport efficiency. Let's talk about band gap tunneling. It is one of the most promising strategies to realize absorption enhancement was a new material synthesis of low bandgap conjugated polymers using electron donor and electron acceptor repeating units. The absorption spectrum of the low bandgap conjugated polymer is shown in the figure 6 over here. There are several issues associated with low bandgap conjugated polymer or PV cells. First, unavoidable reduction of VOC compared with the high bandgap polymer. This occurs because the VOC is related to the energy difference between LUMO of the electron acceptor and the HUMO of the electron donor. Second, to have large enough driving force for electron transfer from the polymer to the electron acceptor. This means the LUMO of the electron donor must be closer in the energy to vacuum than the LUMO of the electron acceptor in order to have enough driving force for exciton dissociation at the interface of the electron donor and acceptor. The strategy for enhancing absorption efficiency of OPV cell is the building of the tandem cell. Since each conjugated polymer has a unique band gap, broad sunlight cannot be harvested efficiently by the single polymer. Therefore, double or triple layer of stacked tandem cell structures are used in OPV cells. Due to this, each layer absorbs a different light wave range and can resolve the limited absorption problem of a single layer devices. However, to fabricate well-performing tandem cells, challenging technical issues should be carefully considered. For example, the interfacial electrode layers located between the front and the back cell could be an issue. The interfacial electrode layer should be able to collect electrons from the front cell, transmit light which will be absorbed in the back cell, and collect holes from the back cell. When the electron and hole collection is not balanced at the interfacial electrode layers, charges accumulate and this lowers the performance of OPV cells. Figure 7 depicts the tandem cell and the incident photon conversion efficiency of the tandem cells. To improve OPV cell performance, concept of bilayer OPV was enhanced by building intermolecularly blended OPV cell with very large interface of donor and acceptors in molecular scale. What is the problem? Blended OPV cell has randomly interdigitated blend layers of holes and electrons which travel long distances before reaching an electrode. This may increase charge recombination chances. Solution to this problem is nanostructured PV cell. This overcomes the charge recombination problem of the blend OPV cell and maintain efficient exciton dissociation. To build an excellently well-performing nanostructured OPV cell, following design steps should be addressed. First, structure should be able to maximize exciton dissociation. Second, the height of the pattern should be tuned to absorb enough photons without losing charges by recombination. Third, the morphology of the capping layer covering the nanostructured pattern may have the importance. When the capping layer is evaporated onto the non-structured pattern, the vacuum deposited layer should cover the pattern bottom layer conformally. When conformal coating is achieved, the interface of the donor and the acceptor layers is able to form a continuous p-n junction. Figure 8 shows a section of the non-structured OPV cell. High mobility semiconducting organics. When the performance of the silicon PV cell is correlated with the mobility issue becomes a critical factor for defining power conversion efficiency. Silicon PV cells can be categorized into A SiPV cell, mu C SiPV cell, and crystalline PV cells depending on the morphology of the silicon layer. The silicon crystals domains are distributed in the matrix. Depending on the crystalline growth condition, morphology and electrical properties can be controlled. The mobility of organic semiconductor provides an important indication about the possibility to improve performance. To improve the mobility of the organic semiconductor, novel material design and the morphology control are promising strategies. To conclude, I would like to say that a lot of efforts have been put in the development and improvement of organic solar cell because of its basic advantages such as environmental friendly, low cost, high speed production. New materials are explored to achieve low band gap. New architectures are designed to improve the efficiency, such as inverted device architecture. Presently, organic solar cells are widely investigated in many directions, such as application of new polymers in the active layer, or as a flexible substrate, or as a buffered layer in the buffered layer of PV devices. A list of references which I have used for my research for this topic. Listening and have a great rest of the day.